All right, so this one says, you draw 2 marbles without replacement from a bag containing 3 green marbles and 4 black marbles. The number of possible outcomes in the sample space is blank. So there are 3 plus 4, right? So there's 7 marbles the first time. But the important part here is it says without replacement. And we're going to talk about this more like as we move further. But without replacement means what happens after you pulled that first marble? You don't put it back, which means now my second pull comes from how many marbles? 6. So that's why it's 7 times 6 or 42. So we're going to talk more about like with replacement and without replacement, but that's one of the things that you want to start to, I feel like once you start to establish like the wording on these questions and the more comfortable you get with them, the easier it's going to be. You're going to look for things like with replacements or without replacements, put back and doesn't put back, because that affects the sample space moving forward. Okay. Today we're going to talk about independent and dependent events. Okay, this is 12-2. Still with probability, everything we're doing from here on out is, okay, but it is independent and dependent events. So the difference between independent and dependent is this. 2 events are independent if the occurrence of one event does not affect the occurrence of the other.
So they're like separate, basically.
Sure. Like you take a marble out of that bag, but then you put it back. The first time will have nothing to do with the second time. Okay? So if you replace something, they're independent events. If you flip a coin and pull a card from a deck, independent events. If you pull a card from one deck and pull a card from a second deck, independent events. One has no bearing on the other, okay? 2 dependent events have the occurrence of one does affect the other. So when we pull that marble out and we kept it, it would now affect the next event. That would be dependent. If you are pulling 2 cards from the same deck, if I pull a card and I keep it, and then I pull from that same deck, those would be dependent events because one is going to affect the other. So we're going to now establish, are they independent or dependent? And then from there, we'll know where to go.
What is the pig?
Example 1 says, tell whether the events are independent or dependent. A box contains yellow and brown dog treats. You randomly choose one dog treat from the box and you don't replace it. Then you randomly choose another dog treat. You're trying for the first event to be yellow and the second to be brown. Are these events independent or dependent?
Independent.
Dependent. Why are they dependent? You do not replace it. So that is, I would say even start underlining, highlighting things like replace or don't replace, because that's going to tell you, okay? So if I took it, I don't know how many, right, because we're not actually answering this question. But for the first event, I would figure out what's the probability of getting yellow out of a full box of treats. And then the second event, I would what's the probability of getting a brown one? Assuming you got a yellow one the first time. So you're always assuming you got what you wanted the first time. So like in that case, there is one less dog treat in that box. So my sample space just reduced by 1. All right, example 2. A jar contains red and blue marbles. You randomly choose a marble from the jar, then replace it. Then you randomly choose another marble. Would these be independent or dependent? Independent because you replace it. So if you flip a coin and you wanted to get tails, does tails then get removed from the coin if I flip it again?
No.
No, which means flipping a coin will always be an independent activity, okay? How about if you roll a die? Independent. Every single time you roll that die, you're starting with a fresh set, okay? If you see the words like a computer randomly generates a number, that is going to be independent because that computer does not eliminate that number, okay? You spin a wheel. There are 2 types of wheels. One is like an actual set wheel, like a game that doesn't change. So it would always be independent. But like if you see one of those digital spinning of the wheels and you remove what you land on the first time, that would then become dependent, okay? So like a digital wheel could start with the same wheel every time and that would be independent. But there are wheels that say remove choice once landed on. And if you remove the choice you landed on, now it becomes dependent. Okay, but most wheels, Okay, our spinners are going to be independent.
Like a fidget spinner?
No, like a roulette wheel. All right, conditional probability is the probability that event B occurs given that A has occurred. So it's called conditional probability. And the symbol for it looks like this. So the probability of B occurring after A has already occurred looks like this. P in parentheses B/A. And so that is the probability of B given A already happened.
How do I do?
2 R's there.
What's that line in front of B?
That's what that symbol means. Given given A has already happened. Mars.
This is only for dependent.
This is no. It could be independent or dependent. Yeah. It's important to know that though because that changes what happens when you go to do B. So you will figure out is it independent or dependent and then move forward from there. But again, you're always assuming A happened. So if the first one was you wanted a brown treat and the second one you want a yellow treat, when you get the yellow treat, you're assuming you already got the brown treat. So one brown treat has been removed. Is it put back or not? That depends on how you get the second one. Kumar.
So example 2 was independent.
Example 2 was independent because you put it back. Yep. All right. Independent events, the way we would find, so these are all and. I want to get a brown treat and a yellow treat. I want to pull a spades and a heart. These are, the wording here is and. Eventually we're going to get to or statements and we do those different. But the wording here is event A and B. So again, and is important. If you want to figure out what's the probability that A and B occur and they are independent, then I find the probability of A and I find the probability of B and I multiply them together. If they are dependent, same wording, A and B, but they're dependent, we find the probability that A occurs and then we find the probability that B occurs assuming A already happened. And still, I'm multiplying them together. And we're going to multiply. So we find the probability separate and you multiply them together. So when we were doing a lot of like the tedious stuff in the beginning, and one of them ones last night, like on the spades one from last night, there's an easier way to do it, which is this. Okay, like the spade one from last night, you got to figure out if I had 13 spades and they went with 13 spades the second time, then it was 13 times 13, right? Different ways that it could happen. That now you're going to simplify it a little bit.
Or 1/4.
Yeah.
Because there's
It was 1/4 and a 1/4. Right. So if you, instead of having to count how many there were, you would have said there was 1/4 to pull the first time, and it would be 1/4 the second time, and you just multiply them together. So instead of having to count them out, now we're just going to multiply. All right, conditional probability now when you're given both. So you can rewrite the formula for dependent events to give a rule for finding conditional probabilities. If I wanted to, like say my original one is finding the probability that A and B occur, if it's dependent, it would be the probability of A times the probability of B given A already happened. That's your normal. So like if the question is what's the probability A and B happen, I would have done it this way. But what if the wording changes to what's the probability B is going to happen given A? If you know the ending probability and the probability of B. So you just take this equation and solve for the probability of B given A. So you're just this little line should not be there. Ignore that.
the one on the side.
Yeah. I don't even know where that came from. Okay. Shouldn't be there. You're just taking and solving this as though it's an equation. If that said like 0.5 equals 1/5 times x, I would just divide both sides by 1/5. That's what this idea is. You're just rearranging your formula to solve for something different. All right, example 3. You spin the spinner shown, which is divided into 8 equal parts. Find the probability you get red on your first spin and blue on your second spin. So the first thing we have to figure out is this independent or dependent?
This
Independent, right? The spinner does not change after the first one. So if it's independent, we're going to find the probability that we get red the first time, and we're going to multiply it times the probability we get blue the second time.
That's 1/8.
How many reds are there? 1, 2, 3, and there's total 8. So 3/8 the first time. How many blues are there? 2 blues. So 2/8. Yep. So you can either multiply them, reduce, or because it's multiplication, it's easier to reduce and then multiply. I'd end up with 3:30 seconds.
Nice.
All right, a bowl contains 36 green grapes and 14 purple grapes. You randomly choose a grape, eat it, and randomly choose another grape. Find the probability that both events A and B will occur. Independent or dependent? Dependent. Hopefully we're not eating it and then putting it back. That would be gross. All right, so I want the probability that the first grape is green times the probability the second grape is green, given a green is already gone. How many total grapes are there? There's 50. There's 50 total grapes. Okay. How many are green? 36. So the first time it's 36 out of 50. And we're going to simplify that in a minute, but for right now we're just going to set it up. Now, one of the green grapes is gone. So how many green grapes are left? 35. How many total grapes are left? 49. If you put it back, now it would be 35 over 50. But because you kept it out, the sample space changes size. All right, what goes in a bowl? 36 and 50.
Wait, I'm quick.
Yeah.
If you put it back, why is it 35?
Oh, if you put it back, it'd be 36 over 50. Sorry. If it was a purple grape you took out and put back, now it'd still be. It would have been 36 and 36. Okay. All right. So what we just said. Divide both these by 2, 18 and 25. And if I didn't have a calculator, I could keep going because 5 goes into both of these. Make it as small as possible. And then 7 goes into this. And I'd end up with 18 over 35. If you have a calculator, you can multiply straight across, but you always have to make sure you reduce at the end.
Final answer.
18 over 35. Mars.
Why can you,
Cross cancel and top and bottom because it's multiplication. So I can go across or top and bottom. I just can't go left and right.
what about like in division?
You would have to flip it.
What's the other green?
Green, given green was already gone. So because it's dependent, you're finding the probability that the green is taken the second time given a first green is already gone.
How did you get the 49 to be 7?
Because it came, like I did 35 and 25 was 7 and 5, and then this 7 went into 49.
Seven times.
All right. Tell whether this situation describes independent or dependent, then answer the question. All right, the first one says a drawer contains 12 white socks, 8 black socks. You randomly choose one sock. You do not replace it. Then you randomly choose another sock. Independent or dependent? Dependent. So we're finding the probability that you first choose the white sock, and then the probability that you choose a white sock given you already chose a white sock. So what's the probability you choose a white sock the first time? 12 out of 20. And what's the probability you choose it the second time? 11 out of 19. Good. So this becomes 4 goes into both those, 3 and 5. And I get 33 over 95. Good. Number 2, you flip a coin twice. What's the probability you get tails on the first flip and tails on the second flip? So flipping a coin would be independent. Probability of getting tails the first flip would be 1/2. Probability of getting tails the second flip Also 1/2.
So that's 1/4.
Correct. Good job.
Easy peasy.
All right, now we get into some charts. So this one says a table shows the number of tropical cyclones that formed during the hurricane seasons from 1988 to 2004. Use the table to estimate A, the probability that a future tropical cyclone in the northern hemisphere is a hurricane. So we are looking at a tropical cyclone in the northern hemisphere. So we're going to narrow it down to the ones in the northern hemisphere. So I'm going to narrow it down to just that first column. And then I want the probability that it's a hurricane. So from here, the hurricanes are just the bottom ones. So it'd be 545 over the total amount of northern hemisphere, which is 199 plus 398 plus 545. And that's 1,142. And I think this in your homework will ask you in decimal format. So this would be 0.48 or 48%. So just pay attention again, just pay attention to what it says to either keep it in decimal form or rounded or percent. B, the probability that a hurricane is in the northern hemisphere. So now we're talking about hurricanes first. Now we're going this way. So the probability that it's a hurricane and a hurricane in the northern hemisphere. So it's still 545, but this time it's out of 545 plus 215, 760. And then 545 divided by 760, 0.712, so 0.72 or 72%. Questions on that one? All right, example 7, you randomly select 2 cards from a standard deck of 52 cards. What's the probability that the first card is not a heart and the second card is a heart if A, you replace the first card, B, you do not replace? So for A, you replace it, independent or dependent? Independent. So I want the probability the first card is not a heart and the second one is a heart, given you pulled not a heart the first time.
So that's 3/4.
So the probability it's not a heart is 3/4. Good. Because it'd be everything but the 13 hearts. And then the probability that it's a heart. So how many hearts are left? They're independent, right? So it doesn't even matter what happened the first time. 1/4 of, well, how many hearts are there? 13. Okay. Out of, oh, so I'm sorry, I don't need this part, and the independent one. Out of 52, which would be?
1/4.
1/4. So 3/4 times 1/4 or 3/16.
That was easy.
Huh?
That was easy.
Yep. Okay, now if you did not replace the card, it is now dependent. So I want the probability it's not a heart, given that you pulled and then the probability that it's a heart, given you pulled a not heart the first time. So same for the first one. Probably it's not a heart is 3/4 or 13 out of 50. No, or what is it? Out of 52. 52 minus 13, 39. Sorry, thank you. Out of 52. So that would have been the same thing. Now, what's the probability? How many hearts are left? If we pulled something other than a heart the first time,
13.
there's still 13 hearts left, but we kept that whatever we pulled the first time. So how many total cards are left? 51. So 3 actually goes into 51, 17 times, and I would get 13 over 68. Questions?
Easy peasy.
All right, homework is on big ideas. Make sure you're showing your work for these. I think there's one in the beginning. Maybe you don't need it, but the rest of them, you need it. I am actually I'm gonna email, no, I just emailed you, actually, the results from the last test, that multiple choice one, not your quiz yet, there's still makeups out for that. But I emailed you that, and then I'm gonna give you back your hard copy so you can get a look out of that.